Sodium circonate as possible materials for hydrogen production in the catalytic decomposition of methane, avoiding catalytic deactivation through CO2 formation, by Carolina Givaudan Pérez, Citlali Cortés Santiago, Héctor Martínez Hernández, Heriberto Faife Perea, and Juan Arturo Mendoza-Nieto, from Mexico City. The great increase in the emissions of polluting gases into the atmosphere, such as carbon dioxide and methane, has become a threat to the environment. In recent years, obtaining non-polluting energy sources such as hydrogen has been proposed as a possible solution. There are already some processes for the production of hydrogen from hydrocarbons. One of them is the decomposition of methane. However, this reaction requires materials that have high catalytic activity and stability for long periods of time due to the accumulation of carbon on the surface. Therefore, in this work, sodium circonate ceramic was chemically modified by the addition of cobalt, iron, and nickel. It was structurally and microstructurally characterized by X-ray diffraction and nitrogen physisorption, and its catalytic activity for hydrogen production was evaluated during thermal decomposition of methane. Thus, the results in the characterization by X-ray diffraction shown in Figure 1 indicated that the crystalline structure of sodium circonate is preserved as the primary phase of the ceramic compound. On the other hand, the results for nitrogen physisorption observed in Figure 2 show type 2 isotherms according to the classification proposed by the IUPAC, related to non-porous materials without the presence of hysteresis. Once the ceramics were characterized, their catalytic activity was evaluated through dynamic experiments in the range of 50 to 850 Celsius degrees. These results are shown in Figure 3 to 6, where it is observed that hydrogen formation is possible from 700 Celsius degrees. With respect to Figures 4 to 6 that correspond to doped ceramics, it is possible to obtain a higher production of hydrogen than that obtained with pure sodium circonate, and the formation of carbon dioxide that contributes to the deactivation of the catalyst by carbon formation. From these dynamic experiments, the best conditions were chosen to carry out isothermal and cyclical experiments. The isothermal experiments were carried out at 4 different temperatures, between 750 and 850 Celsius degrees. These results are shown in Figure 7, where it is possible to produce 25% hydrogen at 830 Celsius degrees in the first 10 minutes of reaction. In general, it is observed that the higher the temperature, the more hydrogen is formed, although it leads to a more rapid loss of its activity. Finally, a cyclical experiment was carried out in which it was decided to add oxygen between each cycle in order to promote the regeneration of the dot material. However, the results obtained is not favorable, since as shown in Figure 8, in general, by adding oxygen, the formation of hydrogen decreases. In conclusion, the doped ceramic allowed to obtain a higher production of hydrogen than the pure ceramic and to avoid the accumulation of carbon due to the formation of carbon dioxide. The highest conversion was obtained at 830 Celsius degrees, and the addition of oxygen between the catalytic stage does not favor the production of hydrogen.